So we are still in stage one in our elastic regime in our stress strain curve. So we're still in that region. But one of the things that we haven't talked about is our two parameters, temperature and time, and strain rate. So why haven't we mentioned these? At no point in any of our equations have we ever come across these parameters, which is strange because you'd think that stress and strain would vary as a function of temperature and time or strain rate, right? At how fast you pull it, the time it takes you to pull it, and temperature. Well, metals and a lot of solid linear elastic materials, stress is not going to depend or strain on these parameters. So we didn't have to worry about them. Uh-oh. It's that time again. Oops, there we go. But we are going to be working with a class of materials, very important class of materials, a class of materials that is near and dear to my heart, linear viscoelastic materials, which encompass the mechanical response of polymers, biomaterials, and a myriad of different composite materials, where indeed the properties are going to change based on time, temperature, and strain rate. And typically, we see that they are viscoelastic, meaning that they will behave both elastically and like viscoelasticity. There's going to be a part that's going to be an elastic solid response, which we're used to before, and a part that will behave like a viscous fluid. So we are going to break down, if we break down these time, temperature, and strain rate, and if we say solid or, basically, I'm going to say break it down into my erasers. Not doing well. There we go. So if I break it down into a solid response and a liquid response or a viscous response, if my temperature is very, very, very low, so you can imagine if I took like a piece of silly putty or polydimethylsiloxane and I put it in liquid nitrogen and then I tossed it against the wall, you can imagine it will brittly fracture. So if temperature is very, 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 very low, I'm going to have a solid-like response or a more solid-like response. If my temperature is very, very high, if my temperature is high in my system or in my environment, then it'll be more viscous or fluid-like response or liquid-like response. Similarly, if my time is very, very, very short, like again, if I throw that piece of silly putty at an extremely high speed, allowing it very, very little time to respond, it will behave like a solid. And if I pull it very, very, very slowly, at long times, it'll behave like a liquid. So you have this basically this property of time, temperature, equivalent. So time and temperature behave in a similar manner. Now, at very, very, very high strain rates, which, because again, a strain rate is effectively a frequency, it's going to behave like a solid. At very, very low frequencies, it's going to behave like a liquid. So strain rate is something that's still related to time, but varies a little bit differently. So the way that we are going to describe the solid-like response is just with our, linear elastic Hookean relationship. But for the viscous response, we're going to introduce a new parameter. And you may have seen this represented like this, shear and viscosity, so viscosity and strain rate, in another course, so perhaps in fluids. So you can kind of imagine, and maybe you've seen this expression before, that you see, or if you have, basically, you have fluid in between here, and I fix this, and I pull this here, we're going to have basically this velocity profile of the fluid. And based on the strain rate at which I pull and the viscosity, eta, of my fluid, my shear stress is going to increase if I pull faster, so my tau, or if I'm pulling through peanut butter versus water, that viscosity will also increase that shear stress. So, pretty cool. Now, you can model this behavior, this linear viscoelastic behavior, with Maxwell models and with Kelvin-Voigt models, using springs and dashpots, where springs denote the elastic response, and dashpots will denote the viscous response. So we'll get into those models in the next video. See you then. Thanks. Bye.